Today we're going to look at the second moment of area and later how that is useful when we look at the theory of bending. Okay, now the second moment of area, or if we just backtrack a moment, we've done centroids so far and we've looked at areas in a previous section. Now the second moment of area, this value denoted by capital I, is going to be useful to us, and we'll show that by means of example fairly soon. But before we get there, let's first understand how we find the second moment of area of a certain shape. Now the first shape we're looking at is this rectangular shape, and we also need to have an axis that we work around. In this very first example, we're going to use axis XX. So this line down here is our axis, and the shape that we are interested in is this rectangle over here. Right, what is the second moment of area? Well, it is equal to the product of area and the square of the distance from the centroid of the area to the axis in question. Now the problem is the distance changes depending where you are in this area. So that's where we go and we slice this shape up into very small rectangular shapes. In fact, they are bordering on infinitely narrow. This del y value is basically tending to 0. So if we read through this, it says the second moment of area of an infinitely small area, that's going to be this rectangular area over here, is equal to the product of its area and the square of the distance from its centroid to the axis. Now the centroid would be over here in the middle of that area. Okay, now the units are meters to the fourth. Let's think why that is. Area is meters squared, and this distance squared is another meter squared. So meter squared times meter squared gives you meters to the fourth. So that's where this unusual unit is coming from. To obtain the total second moment of area of known shapes, these need to be sliced into imaginary thin strips, and the above applied to each slice. So in other words, there are many thousands and millions of slices all the way up here, and we would have to manually do that, which is obviously impractical. Right, so the way we achieve that is by using integration, which you've looked at in your maths studies. But in case you've forgotten that, I'd suggest you go and have a look at this little refresher. Here's a website over here, one of many, where you can actually refresh on integration. So let's get started on this first example of the rectangular shape about an axis through an edge. Starting with the little infinitely thin strip over here, it would have an area of its width times its height. So B is this dimension across here, as you can see, multiplied by the vertical dimension, which would be del y. So the I of the strip, the second moment of area of the strip, would be, as per the definition above, the area times the distance squared from the area to the axis in question. In other words, y times y squared. So we have then b y squared del y. Let's move the constants to the left hand side. Now the second moment of area of the rectangle can be expressed as follows. We've got b y squared dy, and the variable, which is y, remember y changes from nothing to a maximum value of d when it's at its greatest. So the integration is going to occur between limits of 0 minimum and d maximum. So y is at its least at 0 and y is at its maximum at d. So now the constant goes out to the left. There's b is the only one that doesn't vary at all during the process. And then we have the integration symbol, the limits 0 to d, and we are effectively integrating y squared dy. Now from your math studies, you'll hopefully have remembered what happens there. B stays as it is, and in the square brackets, y increases its exponent to 3, and below the line you write the same number. So y squared becomes y cubed over 3, and you write the limits there and there. You then apply the first limit. So wherever you found a y, you replace it with a d. So the b d cubed over 3 is the first value, and then you insert a negative sign, and then you write in the second limit, which would be b times wherever y was is now a 0, And all of that becomes 0, and all you're left with is BD cubed over 3 as being the second moment of area of a rectangular shape about an axis through the one edge. So in simple terms, if you were to know the dimension B of your rectangle, your dimension D of the rectangle, you could very quickly calculate by inserting into this formula over here the two values. You could calculate and you would have an answer for second moment of area of this rectangular shape about an axis aligned with its edge, and the units would be meters to the fourth. Now in a very similar fashion, also a rectangular shape, but now instead of having the axis aligned with the one edge, let's put the axis through the centroid, which we know to be in the middle of that rectangular shape. So we'll apply the same procedure. I of the strip would be B del y, remember what that was? B del y would be its area, the area of the strip, multiplied by the distance from the centroid of the strip, which would be there, to our axis, which is y. Remember that gets squared. And you would do exactly the same as before, except the limits would now be d over 2. Note this way would be half d, or d over 2, and this way would be d over 2 in the other direction. So your limits are negative d over 2 and positive d over 2. Same procedure, the y squared stays to the right of the integration symbol, the constant b goes to the left, and once again you take y squared, increase the 2 to a 3 and place the 3 below the line. And the 3 is now a constant, so it can go and live with b over 3 on the left of the square brackets. And inside you would then apply your two limits. Wherever you found a y, you would put a d over 2, and you would then put a minus sign and your second limit as d over 2. Now minus becomes positive, hence that positive over there, and you're down to b over 3 and a bracket d cubed over 8 plus d cubed over 8, which we know to be d cubed over 4 if you take a common denominator, and you can finally simplify it as bd cubed over 12. Now that is once again a very simple way of finding a second moment of area of a rectangular shape, and by the way, this is one of the most commonly used formulae in the work we're about to do, so you can memorize it as the formula for second moment of area of a rectangular shape about an axis passing through the centroid, bd cubed over 12. Now it's not always convenient to do it always from first principles, so you can look up the I values for various shapes. And the very first one we've just done from first principles is the rectangular shape, and they're using h, we use d, but as you can see it's the same thing. B d cubed over 12 would have been ours. They've got bh cubed over 12, h simply being the vertical height of the rectangle and b being the horizontal. The location of the centroid, you know by now, is halfway up, so that is h over 2, and the area you'd also be able to work out. And then you can look through the table and look at lots of other common shapes. A triangular shape, there's your I formula. A circular shape, one you'll use often, pi d4 over 64. Semicircle, ellipse, semi-ellipse, and finally a parabola. So these are the common shapes you are likely to use in the work we're about to do on the second moment of area. Now here's another handy tool called the parallel axis theorem. If you, for example, have your I value about some axis, you've either calculated from first principles or perhaps you've looked it up in a table, but your problem that you're calculating requires the I to be about another axis. It could be anywhere along the shape. Then you can use this theorem over here, this parallel axis theorem, provided that, and this is something very important to remember, this middle term here must always be an I about the centroid. So you can't, for example, use the parallel axis theorem to convert from an edge to somewhere else. You can only convert from this point, which is an axis through the centroid. As long as you remember that, those are the limitations of using the parallel axis theorem. Okay, how does it work? This allows calculation of the second moment of area about any chosen axis parallel to the axis through the centroid, center of gravity. That's what we said earlier. So if you know that the I of the shape is I whatever, you add to that the area of the entire shape times h squared. Now what is h? That is the distance from the axis through the centroid, that's this one over here, to wherever you want to have the new axis. It could be the edge, or it could be anywhere else that you need the value to be taken around. So just to prove a point, let's go back a step and look at what we just worked out. Remember that the I value of a rectangular shape about an axis passing through its own centroid was BD cubed over 12. We did that from first principles. So let's just hypothetically say we want to now convert that I value to an I about the one edge, which by the way we happen to know already, but let's forget that for now. So let's apply that theory and say I about the center of gravity, or the centroid, is BD cubed over 12, and let's find the I about a new axis, in this case XX, by using the parallel axis theorem, which takes that I value, BD cubed over 12, and adds to it a h squared. Right, so what's the A of the shape? BD, breadth times height. And then we've got to multiply by the distance, remember, that is between the axis through the centroid to this new desired axis, which is d over 2, and that gets squared. Right, so we have BD cubed over 12 plus BD to the 3 over 4. Common denominator 12, and you add it all together, and there it is, BD cubed over 3. Remember that that was the correct, in fact that was the very first one we did, BD cubed over 3 was indeed the second moment of area of a rectangular shape about its one edge. So the parallel axis theorem worked in this example, converting from I through the centroid to I about one edge. So you would seldom use it in this fashion because both of those are known formulae, but if you wanted to, as I said earlier, for example, find I about an axis through here or here, you could use this parallel axis theorem, a very useful tool to use. Let's consider a very simple example of a piece of square tubing being placed in bending by somebody standing at the midpoint, and the piece of square tubing is supported at both ends on bricks as shown. It's clear to see that at the midpoint the square tubing is most definitely in bending. In fact, you can see the deflection downwards. Let's now consider that piece of square tubing that was put into bending as we saw moments ago. So here it is. It is 25 by 25 millimeters in cross section. There you can see that. It has a 2 millimeter wall, and it is 2 meters long, and the midpoint is B, and that's where we applied the 1000 Newton load downwards. Each end would be supporting 500 newtons. That would be to get equilibrium for vertical forces. 1000 newtons at the middle and 500 supporting each end. Now here in the middle is where the most or the biggest bending is going to occur. Now to quantify how much bending is occurring at the middle, we look at the bending moment at section B, and we find that by exposing either the left hand side of the beam or the right hand side of the beam. So effectively you take your hand and you place it at the cross section where you want to work out the bending moment, and you decide which is the easier side, left or right. In this case I'm going to look at the right hand side, so I place my hand on the beam and I cover up all of this, and I leave exposed only this side of the beam, and I say, right, 500 multiplied by 1 meter is giving me a bending moment at cross section B of 500 Newton meters. Okay, now that cross-sectional shape there where the bending is occurring is in fact one rectangle within another rectangle. Okay, so now here's a quick, easy way of finding the second moment of area of that shape. Here is the shape, outside rectangle, inside rectangle. They happen to be squares in this case, but we'll just call them rectangles. And there are the various dimensions, capitals for the outer, lowercase for the inner, with all their dimensions. Now remember, the difference between the outer and the inner is 2 millimeters of wall and 2 millimeters of wall, which is 4 millimeters, hence the 25 and the 21 difference in dimensions. Okay, now let's see what we're going to do here. We're going to go back to our formula for I of a rectangle. See if you can remember BD cubed over 12, or else take it out of the table. Now BD cubed over 12 is I of this outer shape as though it were complete without a missing piece in the middle, and it would be B D cubed over 12. There it is there. Now we put a minus sign because we want to subtract I of this missing piece here, which is lowercase BD cubed over 12. We insert the various dimensions. Remember to work in base SI units of meters, 0.025, 0.025, 0.021, etc. Calculate it, and you find IXX for this piece of square tubing in cross section to be 16.34 times 10 to the minus 9 meters to the fourth. Okay, now for the first time we're going to apply the formula for bending, and here it is here. Sigma is my over I. Probably one of the most important formulae you're going to learn in this course. What it amounts to is the stress in the outermost fibers will be this much, sigma. How do you find it? Well, you take the bending moment, you multiply by y, which is the distance from the neutral axis to the outermost fiber. The neutral axis is the one where stress is 0, which in this case is the center line. Okay, so y is the distance from this axis to the outermost fiber, which in our case would be d over 2. Okay, below the line we have the second moment of area. Okay, that's the thing that you've been working out up till now. That is the number that is measured in meters to the 4 units. Second moment of area about, in our case, the neutral axis. Okay, so if you can find those three values, you can find the stress in the outermost fibers. Okay, what is it we had to work out? Let's go back to the question. When a beam is loaded such that it experiences bending, the stress in its outermost fibers can be calculated for a particular cross-section of the beam, if the second moment of area of the cross-sectional shape is known. Right, for this example, we must consider a 2 meter long piece of 25 by 25 by 2 millimeter walls steel square tubing. Okay, we've done all of that, and the stress in the outer fibers of this very example would be 500. Remember, that was the bending moment which we worked out earlier. There it was there, 500 Newton meters. Okay, that's M, Y, 0.0125. Let's see where that comes from. 0.0125, that's the 12.5 millimeters from the neutral axis to the outermost fiber. That's sorted. And finally, I is this 16.34 times 10 to the minus 9 value. So if you calculate that, the stress in the outermost fiber for this piece of square tubing supporting 1,000 newtons is 382.373 megapascals. Okay, and that would manifest as compression in the top fibers and tension in the bottom fibers, which stands to reason if you were to load the beam over here downwards, these fibers would be stretched, would be tending to be lengthened, and these fibers would be compressed. And incidentally, the fibers on the neutral axis, right on the center line here, would be experiencing zero stress. Okay, so that is one of the uses of this value of I measured in meters to the fourth, a very useful quantity to be able to work out in engineering. Now we get to a slightly more abstract concept, that being the radius of gyration, normally denoted by the lowercase k letter. All right, and it also refers to areas, in this case a sectional area. Okay, so it says if any sectional area A, that's this guy here, whose second moment of area about an axis is I, could be concentrated at one spot K from the axis. Now, of course, that is impossible, but just bear with us for a moment. If it could be concentrated at one spot, distance K from the axis, so that the second moment of area of this concentrated spot is still equal to I, then the distance K is defined as the radius of gyration about the area of the axis. So it's impossible to concentrate all the area in one infinitely small spot. However, if you were able to do it, you would do it at distance K from the axis. Okay, so basically we're going to be using K to indicate, it's another way of expressing I effectively. So the bigger the K for a given area, the better it would resist bending, for example. Okay, so it's just another way of expressing I, as it were. And the relationship between I and K is as follows. I is a K squared. Or if you wish to find K, it would be square root of I over A. Okay, so for a rectangle, Ixx is BD cubed over 12. So K would be I over A inside the square root symbol. There we go. So BD cubed over 12 over BD. We could simplify that a bit further and we could get to K being D over 2 root 3. Okay, now radius of gyration, this new quantity we've just learnt about, can also have the parallel axis theorem applied to it. Just like I values could have parallel axis applied to them, so can K values. However, there is a rider. This term over here must always be K about the centroid or the center of gravity. Okay, very similar to the I values. So let's look at a little example. Find Ixx for the rectangle shown, whose breadth is 0.5 meter and depth 1.2 meters. And we must also find this new thing we've just learnt about, which is radius of gyration. Okay, so first things first, IGG, that's this axis over here, through the centroid would be, as we remember from our table, BD cubed over 12, B being 0.5, D being 1.2, and we end up with 0.072 meters to the fourth. Okay, but now they wanted I about XX. Now note, XX is not even on the shape, it's somewhere distant at 1.4 meters. So parallel axis theorem allows us to find Ixx as long as this value is an IGG, or an I through the centroid, which it is at 0.072, plus area. Remember, that is the cross-sectional area of the whole shape at 0.5 times 1.2. And there is the distance between the axes, 1.4, and it gets squared. So I about this distant axis XX outside of the shape is 1.248 meters to the fourth. So I is AK squared. So K, which is that radius of gyration about the center of gravity, is I about the center of gravity over A square root. So 0.346 meters is the distance to this concentrated spot, this imaginary spot, where we could put all the area and have the same I value. So what that really means is, at 0.346 meters from this axis, GG, there's a spot, an imaginary spot, where if all the area were concentrated, we would have exactly the same I value as before at 0.346 meters. But now we were not asked to find K, or radius of gyration, about GG. We were asked to find K about distant axis XX. And here is where we use the final step, which is parallel axis theorem, but applied to radii of gyration. And if you look back, it was K about the new axis squared is equal to K about the centroid axis squared plus the distance between the two axes squared. So 0.346 is the KGG, and 1.4 is that distance between the two axes in question. And remember, the rider was we had to make this term here a GG term, a centroid term. So to finish off, K, the radius of gyration about axis XX, is 1.44 meters. So what that means is from this axis at 1.44 meters, which happens to be just above the centroid, would be the imaginary position where all the area could be concentrated such that you had the same I value. The question you're probably asking is, why have we bothered with working out I values and K values? What is their use in engineering? Well, they will have a number of uses, but in our case, so far, we've only applied them to bending. So in really simple terms, if you were to look at a cross-sectional shape that was resisting bending, for example, if this was a cross-section through a beam and the bending axis was over here, the higher the value of K, in other words, the further it was to this imaginary spot, the better that shape would resist the bending. Effectively, the stronger it would be in its ability to resist bending. And in the same way, the higher the I value, the stronger it would be in bending. Now, to illustrate that concept a little further, let's look at a real-life example of a beam that is in bending. Now, there is a cross-section through a beam with some dimensions in millimeters given, 30 millimeters, 5 millimeters, etc. And this could typically be, it could be a beam in a factory roof, simply supported at two or more points, and then point loads or uniformly distributed loads, whatever it is, applied to the beam such that the beam experiences bending. Remember, as soon as it experiences bending, the fibers in the one edge will be in compression and the other edge will be in tension. And depending which direction the load is in, those might reverse. Okay, so here is our cross-sectional area, shaded, of a beam of certain length. Okay, first things first, we've got to find a few things. They say it's a section through a steel girder. We've got to find the position of the centroid. Okay, so you know how to do that already from your previous section. Somewhere in here will be the centroid. And secondly, we've got to find the second moment of area of the section horizontally through that centroid. So let's assume the centroid is somewhere there. We would have to find the second moment of area through an axis passing through that centroid. And finally, we've got to find this new thing called radius of gyration about the axis passing horizontally through the centroid. So to find the centroid, let's tabulate the various areas. Well, first of all, let's break this section up into known shapes. And I'm proposing 3 rectangles. There they are. Number 1, number 2, number 3. First rectangle, 0.03 across by 0.005 high, giving us that many square meters area. Second one, that's this one over here, 0.05 by 0.005. Remember, we're working in base SI units of meters, and there's our area of the second one. Third one, that's this one down here, 0.06 by 0.005, giving us that much area. Add up the areas, 0.7 times 10 to the minus 3 meters squared. Right, so that's our 3 areas, as well as the total area. Then we decide which edge we're working around. So in my case, I'm going to use this lower edge as my reference, and I'm going to take moments, area moments, about that lower face. So from the table, 0.15 times 10 to the minus 3 is multiplied by, remember from your section on centroids, the distance from the centroid of piece 1 down to the axis in question. Now I've come up with 0.0575, which is this 57.5 millimeters. Distance from the centroid of number 1 to the axis, the reference axis. Secondly, number 2, take from the table the 0.25 times 10 to the minus 3 times the distance from its centroid to the axis. See if you can agree with the 30 millimeters, 0.03. Remember, these problems, it is vital to have an accurate, clearly labeled sketch. Don't make a mistake on these dimensions, because it's obviously going to render the answer useless. And then the third one, 0.3 times 10 to the minus 3, which is the area of number 3, times 0.0025, which is the distance from this centroid to the axis in question. And then finally, that's all equal to total area, 0.7 times 10 to the minus 3, times the desired distance, which is the distance from the centroid down to that reference edge. We've done this before. Solve for bar y and you find 0.0241 meters, which is in fact 24.1 millimeters. What that means in simple terms, from the reference edge to the centroid, from here to here is 24.1 millimeters. So that has found us A, the position of the centroid. Next is to find the second moment of area of the section horizontally through that centroid. Now to do that, take each piece on its own. Let's start with number 1. I of 1 about its own centroid axis would be this rectangle. What is its I about an axis passing through its own centroid? Its own centroid is depicted with a lowercase gg. Remember, b d cubed over 12 would be 0.3125, 10 to the minus 9 meters to the fourth. That's fine. But now we don't want it about its own centroid. We want it about some distant axis down here. So we need to know how far it is from the axis passing through number 1's own centroid to this new desired axis, which is down here. You've just worked out where that is. And if you do a little bit of arithmetic, you'll find, hopefully, that it is 0.0334 meters to that new axis. Okay, you can check that by looking at the distances that you've just worked out. So using parallel axis theorem, I1 about this distant axis is its original I about its own centroid, there it is there, plus A times the distance between the two axes squared. And you find 167.65, 10 to the minus 9 meters to the fourth. So that is I of 1, not about its own centroid, but in fact about this centroid here. Now you've got to do the same for the other two and then simply add them up at the end. Number 2, this would be a good time to pause and try it yourself before continuing, but anyway, I'll continue. I2 about its own centroid is 0.005 times 0.05 cubed. Remember, BD cubed over 12. And it comes to 52 and a bit times 10 to the minus 9 meters to the fourth. Now comes the parallel axis bit. I2 GG, capital GG. Remember, that's denoting about this axis down here, is the original I about its own centroid plus its area times the distance, very important, 0.0059 being the distance from its own centroid axis to the new one, which is 5.9 millimeters you'll work out. Okay, and that gets squared. So there's your answer, 60 and a bit times 10 to the minus 9 meters to the fourth. 1 to go. Number 3, I about its own centroid axis, BD cubed over 12, no problem there. And then parallel axis theorem, original I plus area times distance between axes squared. Let's have a look where the 0.0216 comes from. Well, that's the distance from this axis to the desired axis, which is 21.6 millimeters you can work out. And finally, you can add the three values together. This one plus this one plus this one is going to give you 369 times 10 to the minus 9 meters to the fourth. So that is I of this entire cross-section about an axis passing through its centroid, which is, by the way, going to be the neutral axis, and you would immediately be able to work out bending stresses at this point. Okay, the question also asked for the radius of gyration about the axis passing horizontally through the centroid. So that should be a simple matter. Once you have I, you know that I is AK squared, and therefore K, radius of gyration, is root I over A. You know I, and you know A. And there it is, 22.96 millimeters would be the distance to the radius of gyration from an axis passing through the centroid. Now, some good news, there are other ways of finding K and I other than by working it out. You can use a CAD system, and provided you get the axis in the correct position, you can request the CAD system to give you K values and I values. A little bit indistinct here, but there they are. That's software called Rhino being used to find I and K, but virtually any modern CAD software can work these values out for you.